Below is a summary of 97 World Series championships and the number of games that were played in each series. To win the World Series, a team must win the most games out of 7. So, for example, if one team wins the first 4 games, the series ends at game 4. If one team does not win the first 4, the games continue until one of the teams wins 4 games. Therefore, the length of each series differs every year. Let's look at the data now. So in this, we've summarized the games when they end at game 4, 5, 6, or 7, and observed of the 97 times, for example, 18 times the series ended at game 4. 37 times the games ended at 7. Okay. Now, here are the expected proportions. So it's expected that 2 out of 16 times the series will end at game 4, and 5 out of 16 times that the series will end in game 7. So what we're going to do is do a goodness of fit test and test this claim. At the 5% significance level, let's test the claim that the 7-game series occurs more often than expected. So first we'll start out by defining the null and alternative hypothesis. I've done that here. The null hypothesis is just the expected proportions listed from here, so I've recopied it. Now, we're claiming that the 7th game series occurs more often than expected, and that's really what our alternative hypothesis is that the probability, the fourth probability that corresponds to game 7 is not 5 out of 16. In fact, it's actually greater. But a simple way to summarize this is just to say that at least one of the proportions is not equal to the stated value. So let's state the significance level of the test and the type of tail. So here we are told from our problem that we're looking at the 5% significance level. This is the goodness of fit test that will use the chi-square distribution, so those are always right-tailed. The degrees of freedom are the number of categories. We have 4 categories, games 4, 5, 6, and 7. So the number of categories minus 1, in this case, is 3. Then we'll need to determine the critical value. So for that, we will look for the, we'll use the chi-square. Oh, we have to tell it equals. All right, we want the inverse and the right inverse. So to the right, we want 5%, 0.05, 0.05, okay, comma, the degrees of freedom are 3, close your parentheses, and click OK. So there's our critical value, 7.81. Next, we need to determine the test statistic, and this is a bit more involved, so I'll come over here. So remember, our chi-square test statistic is going to be, it's going to look at the distance between the observed and expected values. So I've just recopied our categories in column form to make it easier for us so we can do fills to do the calculation. So games 4, 5, 6, and 7, the data 18, 20, 22, 37, and the expected proportions were filled in. Now, if we're going to look at the observed values minus the expected values, the observed values are in terms of the number of games, so we need to translate this expected proportion into an expected number of games. So the expected number of games that would end, our series that would end in the 4th game, will be equal to, there's 97 games, and times this proportion, which is in G22, and click OK. And now we have an expected number of games. Okay. Now we want to fill this. If you're on your computer, you can just pull down. I'm on my tablet, so I'll have to say, go ahead and fill before I pull down. There are the expected number of games. All right, now let's begin calculating the test statistic. We'll do it in stages. First, we're going to calculate the observed minus the expected, then square that value, and then lastly divide by the expected. It'll just make things a little bit easier to do it in steps. Okay, so here we go. The observed minus the expected. We observed 18 games. We will subtract off the expected. Now remember, use the expected number of games, not the expected proportion. And click enter. Now let's fill this. So there are our observed minus the expected. Now we want to square those values, so we'll take this and square it, and then we'll fill for the rest. And then lastly, we can take and divide that by the expected number of values. So we'll take this cell and we want to divide it by the expected, again, expected number of games, not the proportion. Click enter. We will do that for all of them. Oops, gotta fill it first. Fill, now pull down. All right, there we have it. Now the chi-square test statistic will be the sum of all of these. So we'll let Excel calculate it for us. It'll be the sum. Go ahead and highlight the range. Okay. Close your parentheses. I gotta fix some of this. You just want it to say the sum of the range. And then click OK. And there it is. This is our chi-square test statistic, 7.35. All right. So let's come back over here. That's what we were looking for. Let's just copy that to this cell. We want this to be equal to, and we found it in this cell. So there we go. Click enter. All right. So now we have it in a nice summary. So now we just need to calculate the p-value associated with this. So this will be equal to the chi-square distribution. We're calculating the chi-square distribution on the right. Here is our test statistic, comma, the degrees of freedom, which are 3. Close your parentheses and click OK. And that's it. That's all we need to know. We can now make the conclusion of the test. If we look at this p-value of 0.06, this is greater than alpha, which is 0.05, our significance level. So based upon that, we will not reject the null hypothesis. We could also do it, make our conclusion based upon the critical value. Our critical value, that is the boundary of the critical region, is at 7.18, while our test statistic is 7.34. So 7.34 is less than 7.81. It is outside of the critical region, and so in either method, we will not reject the null hypothesis. Okay. And then if we want to we'll interpret the conclusions of this test. Right, so I'll just come over here again. We have this summary of everything that we did. And if we were to interpret the conclusions of this test, we could say at the 5% significance level, there is not sufficient evidence to support the claim that a 7-game series occurs more often than expected.